Here we are in the last chapter, chapter 7, for exam 2. We are skipping chapter 6 on thermochemistry, which is covered in 152. Now, chapter 7 concerns, bizarrely, since we're so far into the book, the electronic structure of atoms. How are atoms put together? It involves a little bit of physics with quantum theory, and it involves a little bit of a history lesson with how we got to our current understanding of what the structure of an atom is. Now, this is still ongoing theory. In fact, just last week, this is recorded in October of 2017, just last week, there was an article that appeared about the electronic structure of oganesson, element 118, which says that everything that we know so far about where electrons are in atoms is not true for this new element. The nucleus is so big that all bets are off with this. So it's an ongoing and evolving theory. That being said, it works pretty well for the main group and the transition elements and the intertransition elements, for the most part, to explain their chemical behavior. Now, that being said, we'll learn about all of this structure and where the electrons are and so on and so forth, but in the end, what really matters is how many outer valence electrons an atom has, and that's it. That's it. The alkali metals have one valence electron, the alkali earth metals have two valence electrons, etc. across the main group, skipping the transition elements, to 8 for the noble gases, or 18 if you're counting the transition elements, so for the heavier elements. So we can learn about all this structure, but in the end, Mendeleev was able to set up the periodic table, and Meyer was able to set up the periodic table the way that they did, because the reason that elements behave chemically the way they do is because of the number of outer or valence electrons. And all the rest of this, you can't have an outside without an inside. In 127, I don't even discuss the inside electrons, and we pretty much ignore the nucleus except for one little section in 127. In 152, you can do some nuclear chemistry, but even that, it's a small subset of chemistry. The nuclear chemistry, messing around with the nucleus, is not something that is done in everyday life. The chemical reactions that happen in your body, in the environment, all are valence electron chemistry. They don't ever mess with the nucleus, and that's why the alchemists always failed. But they did discover pretty much all of modern chemistry. So we'll kick off chapter 7 with a bit of a physics lesson and talk about waves. The reason that we're talking about light at all is because we use light to discover stuff about atoms, molecules, ions, and chemical reactions. We can use light, whether we're seeing it visibly with our eyes or using a different wavelength of light, to investigate or interrogate chemicals. So what is a wavelength? Well, light travels in waves, as you see here, and the distance from peak to peak is a wavelength, all right? Not peak to trough, all right? That's only a half wave. And half waves, they used to be more important when antennas for radio signals were not digital. Because if your antenna was a full wavelength or a half wavelength or a quarter wavelength or some multiple thereof, then you got a better signal. But these days with digital technology, the length of an antenna isn't as important. So anyway, light traveling in waves, which has a perpendicular magnetic and electrical component, travels in waves. All right, and we have wavelength, and there you go, there's your science definition. Amplitude is how high the wave is. That's the power of the wave. 50,000 watts of power would have a higher amplitude, okay, for your favorite radio station. But we don't deal with power of waves at all in chemistry. We only deal with the energy of a wave. And the energy of a wave is, perhaps surprisingly, given the whole power discussion, corresponds to the wavelength. If you were just standing here, maybe I'll draw a little stick figure, because why not? It's early enough in the day to do a little artistic drawing. Right, so if I'm standing right here, okay, smiling. All right, this longer wavelength wave versus the shorter wavelength wave, more of these waves will pass me in a given amount of time, given that the speed of light is constant through a particular medium. Speed of light 3 times 10 to the 8th meters per second in a vacuum. It's different in air and different in water and so on and so forth. But regardless, a longer wavelength wave is going to have fewer waves passing a given point in time than a shorter wavelength wave. And that affects what is known as the amplitude, the frequency. Amplitude's already on screen. The frequency, the number of waves that pass at a particular point in a unit of time, and we usually use a second. So a hertz is an inverse second, a second to the -1, a 1 over seconds, okay, as is shown here. But s to the -1 is the same thing as 1 over seconds, all right, and that's the same thing as a hertz, Hz, for the scientists that came up with this concept. So frequency and wavelength, right, are directly correspond to each other. The longer the wave, the longer the frequency, because there's fewer of those waves passing in a given point in time. Both wavelength and frequency, therefore, correspond to energy, not power. We don't deal with power at all, okay? Speed of the wave would be the wavelength times the frequency, and that speed, again, is going to be 3 times 10 to the 8th meters per second, at least in a vacuum, although not particularly useful for us. What is, I think, valuable to look at is the entire electromagnetic spectrum, which is shown here, sort of, because I don't know why your book leaves this out. I'm sure there's some, perhaps, decent reason, but cosmic radiation would be out here, the highest form of radiation. I guess this is perhaps terrestrial radiation as opposed to deep space radiation. In any case, we've got high energy, okay, which is a very short wavelength, notice, and a very long frequency, okay, out here. Very high frequency, lots of waves pass in a given amount of time per second because the wavelength is so short. Down at the opposite end of the spectrum, we've got low energy, and of course then a very short frequency. Not that many waves will pass in a given amount of time. Remember, the light's traveling very fast because the wavelength is so long, 10 to the 13th nanometers. So 10 to the 13th times 10 to the 9th, because 10 to the negative 9th for nanometers. 10 to the -9, okay, is a nanometer. So all these 10 to the whatevers are multiplied by 10 to the -9th because a nanometer is very short. Okay, so let's start with the high energy ones. All right, cosmic radiation we'll ignore. That's deep space radiation that is coming from the sun, other deep space sources, black holes and so on. Well, not a black hole because nothing escapes, but anyway. Gamma radiation is the highest energy form of terrestrial radiation, and this highest energy, okay? Meaning, if Dr. Bruce Banner had blasted himself in the brain with gamma radiation, he would not have turned into the Green Incredible Hulk. He would have turned into dead, because what you hit with gamma rays dies. It is that high energy. You hit it, if it's hit either doesn't even have to absorb the radiation. Gamma rays just passing through it will leave so much turbulence in their wake, it will kill it. All right, this is why gamma knives are used in cancer treatment, because if you blast a tumor with a gamma ray, it will die. If you blast regular tissue with a gamma ray, it will die. So you have to target it very carefully. And with the development of gamma lasers, we've been able to do so. So a friend of mine who unfortunately contracted esophageal cancer, which is usually a fat old person smoker's disease. He's a vegan in his 20s and thin. Anyway, he went for a lot of alternative treatments, but he also got a gamma knife treatment, and they killed the tumor, and he beat it, which is good because you don't often beat that one. In any case, the next lower in energy is X-rays, and this is why you don't want to get too many X-rays. The energy is so high, it goes straight through your skin and gets absorbed by the bone. And of course, red blood cells are produced in bone marrow, and so, you know, you've got this high energy radiation being absorbed by the place that gives you your red blood cells. You get too many X-rays, you're going to end up with leukemia. As a firefighter, I was at the World Trade Center on 9/11, and so I'm in the World Trade Center Health Project, and I go in for a chest x-ray every year, and honestly it makes me a little nervous because they're screening me annually for lung cancer using something that could potentially give me cancer. But it's the only x-ray I get every year usually, other than maybe a dental x-ray every now and then. So we're all right, and they cover you with the leads to protect the rest of your body. In any case, the reason you don't want to get too many x-rays is because they are very high energy. Next lower energy from that is UV radiation. When you go to the beach, you got to protect your eyes or protect your skin with sunscreen from the effects of UV rays. UV energy is strong enough to break bonds, to take the atoms that are linked together with strong chemical forces, bonds, and break them apart from one another. Okay, you got to protect that. You don't want to break bonds. You don't want to oxidize your skin or burn your skin or age your skin. All these things are the same word, are the same thing. They're all oxidative processes, and breaking bonds can often be oxidative. Next lower in energy is visible. This is the stuff that we see with. Now, there used to be like a little drawing on here that I just showed that this is an expansion of the visible region. It goes from 400 to, I don't know why they wrote 700, 800 nanometers is the generally accepted region of visible light. 400 to 800 nanometers. How do you remember which end is which? Well, short wavelength is high energy. Long wavelength is low energy. UV, sunburn. Infrared, other side of the spectrum, is where you warm your hamburgers at the fast food joints. So red is down here because it's low energy, near the infrared. Violet is up here because it's near the UV. So violet end of the spectrum is the 400 spectrum, and 400 nanometer end of the spectrum, and 800 nanometers is the red end of the spectrum because it's down near the infrared. Okay? So infrared keeps your hamburger warm at the fast food joint. I'll leave it all the writing up there. Lower in energy than infrared is microwave. Now think about this. This is weird. Microwave radiation is lower in energy than visible radiation, yet we use it to cook our food. And this is because of interesting discoveries in science that you can use specific wavelengths of light to interact with matter in specific ways. Infrared causes not atoms to break apart that are joined together with bonds, but it causes them to vibrate. And they can vibrate like this, they can vibrate like that, they can vibrate like this. There's all different modes of vibrations, but infrared just causes the atoms to vibrate around their bonds. In ultraviolet, breaks them apart from each other. Microwave causes molecules to spin, the entire molecule to spin. And what our microwave ovens are tuned to is the spinning frequency of water molecules. So you can't cook dry pasta in the microwave because there's no water in it. You try it. It might heat up a little bit if your pasta is not completely dry, but it's not going to cook because there's not enough water in it. The story goes that an Army researcher studying microwave radar in World War II had a Hershey bar in his pocket and was playing around with the microwave machine, and it melted the candy bar in his pocket. He thought, well, that's unusual. Maybe we could use this for a civilian purpose, and the microwave oven was born. A lot of stuff has come out of Army research that's actually beneficial for mankind and doesn't involve blowing people up. But microwave energy, lower in energy than visible, lower even than energy than the lights that keep your food warm. Okay, you can cook food with energy that's lower, with radiation that's lower in energy than just stuff that keeps it warm, because of the way it interacts with matter is completely different, vibrating bonds versus spinning molecules. Lower than microwave, or actually right in the microwave region, is cell phone energy. Okay, so you've got a microwave generator up next to your water-filled head. Is this spinning the water molecules in your head enough to cook them and cause your brain to get cancer? With as many years now as we've had cell phones, I think if it was going to cause a major spike in brain cancer, we would have seen it, and we haven't. So probably not. Seems like cell phones are pretty safe. There are still people out there that say they're not. So be it. Lower in microwave is radio waves. Okay, radio waves, very, very, very long wavelength, very, very, very low energy, very, very low frequency, because not that many waves can pass you in a given amount of time. All right, so that is the electromagnetic spectrum, and we've taken advantage of the fact that we can use different regions of the spectrum to interrogate matter in different ways. Oh, there's my little lines. All right. I present this story to you just because it's a very interesting deal with the scientific method. So if you saw the movie The Dish, which came out in 2000 with Sam Neill, it was a story about a radio telescope in the middle of nowhere, Australia. And the reason it's in the middle of nowhere is because they're looking for signs of life from space, signals from space that could indicate an intelligence out there sending these signals. And they, the guys at the Parkes Observatory found a signal a few times, first starting in 1998, that they couldn't explain. And an unexplained, semi-intelligent signal from space is very interesting. And it's been detected like one or two other times by other observatories around the world. And they kept trying to figure out what the signal was because they kept seeing it over the years and over the years. And in January 2015, they discovered the source of the signal. And it turned out that if you were popping popcorn in the microwave in the break room at the observatory and you just opened the door without turning the microwave off first, it emitted the signal that they were detecting. So they were a little bit embarrassed about this, I would imagine, yet they still published their results as a very, stodgy paper. We discovered this signal and we were tracking it down for 15 years, and we localized the signal source to be the microwave oven in the break room. And they published it in the notices of the Royal Astronomical Society. Now, there are still, again, other observatories that have observed the signal, and a couple of times at the Parkes Observatory even, where they discovered they recognized the signal without anybody using the microwave, as far as they know. So they're still looking for peritons, a 10 to the 9th hertz signal that is unexplained, both from microwave ovens, if you rip the door open without turning it off, or perhaps from deep space. What's bizarre is that they had the same microwave at this Parkes Observatory for 15 years, I guess. Anyway, there you go. So light, Maxwell, 1873, perpendicular electric field and magnetic components, and electromagnetic radiation is exactly what we've been talking about. Speed of light in a vacuum, 3 times 10 to the 8th meters per second. I guess I could have had this earlier. And wavelength times frequency equals the speed of light. What do we use this for? Again, studying matter because of the way that it interacts with matter differently. Now, Planck was a guy who saw an interesting phenomenon with matter and needed a theory to explain it, and so Planck gave us one. So the heated solids problem. You've seen this, I'm sure, on TV or maybe even at home. If you take a safety pin and you put it in into the flame on your stove to sterilize it for medical uses or whatever, that it gets red hot. When solids are heated, they emit electromagnetic radiation over a broad range of wavelengths. The light bulb, you energize the tungsten filament and it emits light over a broad range of wavelengths. How come this is true? Why do light bulbs and heat lamps and glowing pieces of metal emit radiation at specific wavelengths? Well, it depends on the energy in. The energy in influences the energy out, and Planck figured this out in 1900. And his explanation was that light is quantized. Light is emitted like in packets of light. Packets of light. Now, I have a hard time visualizing what a packet of light would look like, so I'm not even going to give you a drawing of a packet of light. We saw what the waves look like, but that wave, it doesn't have a starting point and an end point. It just, keeps on going. The way I visualize it is like a couple of waves is the packet of light. Honestly, this is all physics, and we could go very, very quickly here. Sorry, I've been rambling for more than 15 minutes on this. But he related the energy to the frequency. So energy equals Planck's constant, h, which is given down here, times the frequency, nu. This is not a v, it's a v with the tail on it, nu. Or that it's Planck's constant times the speed of light divided by the wavelength. So this is why wavelength times frequency equals speed, or speed over wavelength equals frequency from this equation. We won't use this much, to be honest, but here's Planck's constant, 6.63 times 10 to the negative 34th joules, a unit of energy, times seconds, so that everything all works out nicely. Energy is in joules, Planck's constant is in joules seconds, frequency would be in hertz, or this would see speed is in meters per second, and this is in meters, so you get the idea if we needed to manipulate this, which we won't. Honestly, that is the end of section 7.1. I thought we were going to do another mystery, but I guess the mystery is in section 7.2, which will start whenever you click that button.